Okay, good morning, ladies, gentlemen. It is my great pleasure, I almost sound like a barker there, but it is indeed my great pleasure to introduce today's speaker, Jeff Duerk. He is he's currently chair of our biomedical engineering department. And I'd like to just tell you a tiny bit about his terrific background. He got his BS at Purdue, his MS at Ohio State, came to Case, got his Ph.D. in 1987. I commented that he seemed in pursuit of that perfect football school as he moved along there, as we're currently 8-0. Okay. He actually was working at Picker while doing his Ph.D., and that's the period, I think, when I first met Jeff. He then moved into the faculty at Case, and that was 1988?
89.
Okay, 89, okay. And originally in the departments of radiology and biomedical engineering, he has had a tremendous impact in the whole field of MRI imaging. He's a member of 2 editorial boards. He's a fellow of the International Society for Magnetic Resonance in Medicine. He's the past president of that same society. And it's pretty impressive that that society has 4 Nobel laureates in it. He's published over 150 peer-reviewed manuscripts. And he's not just a theoretician. He's got 12 patents, 15 patents pending, 30 invention disclosures. So he keeps pretty busy there. And let's see, he's co-leader of the Development Therapeutics Program in the Cancer Center. Jeff, have I left much out?
That's pretty complete.
All of those many students also that you've advised over the years.
Right, right. Well, thank you very much, Frank, for the introduction. One of the interesting things for me is coming to medical imaging many, many years ago was the fact that I came to it, you know, from a perspective that's much like your own. But before I begin, I want to thank Moran Margani for the invitation to speak to you, the Electrical Engineering Computer Science Department. I'd also like to thank my friend and colleague Mark Griswold, who's an associate professor in radiology and one of the fathers of parallel imaging that we'll talk about here in a little bit later, as well as Nicole Cyberlick, who's a postdoc with Mark, and Jamal Derakhshan, who is a future MD PhD but is currently a PhD candidate working in my lab. So as Frank pointed out, I sort of have the traditional electrical engineering background. I went to Purdue and graduated in 1981, basically much like many of you guys do, looking at signals and systems and analog and digital circuitry. I went on to Ohio State, got a master's degree in electrical engineering in 1983. And it was during this last few months in my master's program that I heard what I thought was one of the most compelling lectures I had ever heard. It was about a new medical imaging technology called nuclear magnetic resonance imaging, what we now know as MRI today. And basically following some brief stints in the defense industry when I worked on massively parallel processor design, I began to think about how I might be able to exploit sort of my background in electrical engineering and all the things I had learned in terms of signal processing and circuit design and digital electronics and that kind of stuff to do something more useful than building massively parallel processors for building better bombs. But what I want to say at the start is essentially I'm one of you. I really think of myself as an electrical engineer by training. And it was only after that, sort of when I came here to Case Western Reserve in 1983 and got my PhD in 87, that really at the time Cleveland was one of the world's hotbeds, and it continues to be a hotbed for medical imaging research, not just on this campus, but industrially as well. The big vendors, for example, in MRI are basically all located here in northeastern Ohio. Philips Medical Systems out on Minor Road, GE, Toshiba, Hitachi, they all have facilities here in Cleveland because of the unique culture that exists here. So I returned to the faculty at Case in 1989 and really, after leaving industry, the medical imaging industry, wanted to see if we could sort of push the development of this field forward. So medical imaging really started back in the late 1890s with the discovery from Wilhelm Röntgen of the discovery of X-rays. And this is one of the first images that we have here on the left of Röntgen's wife, and I want to note the wedding ring. One of the other things you'll note is the fact that if you go through the archives, and Mark actually did his PhD in Würzburg, is I think there are no examples of Röntgen with an X-ray image of Röntgen himself. He was a little perplexed by this new technology that he discovered and was a little bit afraid of it. And as far as I know, there's no images actually of him. But only 4 months later, 4 months after the discovery of X-rays, here in Kenyon College, Ohio, is another X-ray image that really sort of notes in this article, or in this note that was sent on back to the folks in Germany, that this particular exposure that was taken here in the Cleveland, Ohio area 4 months after Röntgen's discovery was basically on a judge, and is one of the first demonstrations of a physician and a physicist partnership in imaging research, in which the physician notes that it took a 40-minute exposure using a static machine and a waterfall to provide the electronic power to drive the X-ray tube that was used to make this exposure. But that was the lengths that people were going to in those days in order to capitalize on some of this technology. If we look at sort of where MRI fits into this whole perspective, as late as the 1950s, essentially didn't exist at all. However, in 1946, the phenomena of nuclear magnetic resonance existed, and people were using it for chemistry and to look at chemical structures and that kind of stuff. But using it for imaging didn't even exist in the 1950s. And that didn't occur until 1972, when the whole idea of the first concepts of magnetic resonance imaging existed. 9 short years later, as the technology evolved from the concept of imaging to clinical practice, University Hospitals in Cleveland was one of the first institutions worldwide to have this new technology. And this is one of the things I want to sort of bring out in the course of this lecture, is the fact that Cleveland, Ohio, in this area has always been a hotbed for adopting innovation in new medical imaging technologies, going back as far perhaps to Röntgen's discovery and 4 months later it being used here clinically. But only 9 years after the discovery of MRI, or the concept of MRI, and shortly after the first whole body systems were available, this city began adopting that technology for clinical use. And in fact, in 2005, our research group was one of the first in the world to have, in fact, one of the most innovative systems available today in terms of MR. This is both a short bore and a wide bore MR system. There's only two of these specific kind of systems available in the world. So let's go back and look at another imaging technology for just a second, so I can sort of continue to highlight how Cleveland pushed the innovation of some of these fields. The first whole body CT scanners that use X-ray technology came out in 1972 from a company known as EMI. And who knows what EMI stands for? Electronic Musical Instruments. Okay, and you may say, how is it possible that a company that makes musical instruments came up with the first CT scanner? Basically, perversity of nature, and it happened. In 1975, some of the first clinical CT scanners, again, were adopted here in the Cleveland area, and within 3 years of their coming to Cleveland, our former chairman of radiology, John Haga, performed the first CT-guided biopsy of a tumor. Now, this is notable in that today, CT-guided biopsies, or image-guided biopsies, are routine, and the first ones ever done in the world were done right down the street. So the technology in the span of basically 20 years went from the image quality you see on the left in terms of the CT scan to what we have today, where you can see the liver, the spine, kidneys, etc. Another thing is, from Röntgen's era, we knew that we could do projection images in a sagittal plane, for example, and look at, for example, the kidneys and the spine and things like that. With the advent of CT scanning, we knew that we were going to have multiple slices. And using some technology that was available back in the 1970s, computer scientists took that stack of slices and were able to artificially create a sagittal scan from the thick slices that were acquired with the CT scanner. Today, however, using that same technology, you can see the improvement in the image quality as the scan slices, or the slice thickness, got much, much thinner. So it's this partnership that I want to get across between physicians, between computer scientists, between electrical engineers, that pushes the innovation forward. Physicians said, we would like to have the same type of scans that we have with our X-rays, but have them in a tomographic mode, a slice, instead of a projection through the whole patient. Using some computer science techniques, the first sagittal CT scans were made, and this is now what we have available just 20 or 30 years later. The other thing we can think about is different modalities provide different information. In the case of PET scanning, positron emission tomography, we actually get metabolic information as well. So while we may not have particularly high resolution images, as you can see here on the right, what we do have is fantastic functional information about the metabolism of glucose. What we're essentially doing is creating a radioactive version of glucose, giving it to the patient, it distributes systemically, and those areas that are metabolically very active take up that glucose analog, create high concentrations then that contribute to the image. So the PET images gives us functional information, but not very good resolution. But by combining the PET scanner and the CT scanner together in one instrument, we get the best of both worlds. That is, the high-resolution CT scan and the metabolic information from the PET scan. That again, using some techniques from our computer science friends, merge those things together to get the best of both worlds. That is, high-resolution CT scan with the lower-resolution metabolic information together. Now, as I said before, Northeastern Ohio is really a hotbed for medical imaging research, and I just want to bring out a couple examples of that. Paul Lauterbur, who is a Case grad in chemistry, won the Nobel Prize in 2004 for the development of the idea of magnetic resonance imaging. Secondly, there's a number of things that we use that technology for, both in patient scanning, but also in sort of the translational research opportunity. That is, mouse models of disease before we even go into human settings. And in here at Case Western, we're one of the 8 institutions nationwide that are a small animal imaging resource program. Similarly, as I mentioned before, the medical imaging industry here in Northeastern Ohio is really a large employer. I think there's over 2,000 people employed in the medical imaging field here in Northeastern Ohio right now. And as you can see in the Plain Dealer, for example, there have been a number of articles over the years that have sort of capitalized and expressed how important it is for this region to create sort of an imaging hub, if you will, or to capitalize not just on our ability to make steel and car, but also new technologies like medical imaging. So for the rest of the talk, I'm really going to focus on magnetic resonance imaging, which is Mark and my specialty. And what I'd like to talk about is the fact that while this technology didn't exist in the 1950s, and we have some capabilities today, I want to first give you an introduction to sort of how does MRI work, so you sort of understand as we talk a little bit later what some of the technologies are involved and how it may be relevant to you guys as electrical engineers or computer scientists. Basically, MRI is based on detecting the NMR phenomena. That is, inside the water molecule are 2 protons, 2 hydrogen nuclei, each with a little magnetic moment. And by transmitting through a radio frequency coil or radio frequency signal into the body absorbs that radio frequency energy, the proton does, it excites the protons, and we'll get into more detail on this, and they then re-emit that signal back to us. So right away you should be thinking, gosh, I know I'm going to need some way to create a radio frequency pulse that's going to go out into the body, so I'm going to need amplifiers and some type of coil or antenna to create the magnetic field. As the body re-emits it, I'm going to need detectors to pick up that signal. I'm probably going to need to digitize it and that kind of stuff. And we're going to talk about all these different things. One of the interesting things is to create that transmission or to create that radio frequency field to start with, I need in the order of kilowatts of energy. You know, thousands or hundreds of volts, for example, and hundreds of amps going out into some particular coil to create that field. And yet the signal that I get back may be only nanovolts in strength. So that same coil that I'm going to use to send out that pulse, a few microseconds later, I may need it to switch from being in the hundreds of volts range into the nanovolt range with excellent sensitivity and excellent signal to noise. And we're going to talk about some of the ways we do that. So I put a little asterisk down here in terms of the timeline, in terms of what MR image quality has done over the last 20 or 30 years or so. I got in the field in 1983 and the image quality was somewhere in between this image you have here on the left and this image over here. But over those 20-some years or so, the image quality has changed from this to this, and our scan time has gone down to 1% of what we did years ago. When I got in the field in 1983, it was not uncommon for a patient to come into a magnet and take 25 minutes for it to get one set of slices of a brain, for example. Today, we routinely do that in less than a minute and a half. And we have this type of dramatic improvement in the image quality as well. And we'll talk about some of the technologies that come into play and how they're relevant to electrical engineering. Well, with that kind of change in image quality, that also opens up new opportunities for us. Previously, it would have never been thought of to try to use MR imaging for image-guided procedures, to actually go in and treat cancer where it sits, to take a biopsy of a tumor, or to treat it thermally and kill the tumor actually where it sits inside the liver. Now we do this routinely, both in animals and patients over in our lab at university hospitals, because we have the ability to image fast, get high contrast between the tissues, and to monitor the changes in the tissue in response to temperature. And further, we can do other things like look at functional activity of the brain. The fact that while we're thinking, while you're listening to my lecture, for example, and you hear that loud bang, part of your brain gets activated because you were startled. In MR imaging, we can actually detect that activated region of the brain and create images that show not only what regions became activated, but also what regions of the brain are connected. So this image on the left is what we're looking at here is basically the fiber tracts in the brain associated with the white matter in the brain. That is the white matter fiber tracts associated, for example, with multiple sclerosis and diseases like that. All of this is possible by the increase in performance we've gotten over the last few years. So I want to tell you that this diagnostic imaging modality called MRI basically is unlike almost anything else that we have in the radiology department, and that is it uses no ionizing radiation at all. There's no X-rays involved in MRI at all, okay? There's over 13,000 units available worldwide, so it's an incredibly well-adopted imaging technology, and approximately 40 million scans are performed each year. So it's got a high safety profile, it's around everywhere, and it's a very safe technology as well, no ionizing radiation. And as I said before, the concept of imaging came up with in 1973 by Paul Lauterbur, who shared the 2003 Nobel Prize in his previous association with Case. So MRI is really a story of coils, okay? Different kind of coils that I'm going to talk about today. We're going to talk about coils of wire that have current in them to create the main magnetic field that we're going to talk about shortly. We're going to talk about gradient coils to change that magnetic field in a linear way in a temporally dependent manner so that I can turn on a variation from head to foot, from left to right in the strength of the magnetic field. There's going to be other coils I use to transmit radio frequency and coils that I use to receive that radio frequency back. And we're going to go through some of the different technical specification and characteristics of each of these different kinds of coils. So let's talk about the first one. That is, in magnetic resonance imaging, we need a really strong magnet. And we're going to talk about why that is in just a couple seconds. This magnet that we use in MRI basically has about a 1 meter bore. So it's big enough for us to get inside of. It's actually about twice as large as, the bore size is about twice as large as what we need to get somebody inside of it, because there's actually a bunch of additional electronics that I need to pack inside of the magnet before I slip the patient inside. A typical magnetic field strength for MRI is about 1.5 Tesla, and who knows what a Tesla is? Okay, and 1 Tesla is 10,000 Gauss. What's the strength of the magnetic field right here in Cleveland? Half a Gauss. So these fields that we're using in magnetic resonance imaging are 30,000 times stronger than the strength of the magnetic field here in Cleveland. And we're going to create this magnetic field with basically a large static electromagnet. The other types of fields we're going to look at are the linear gradient magnetic fields. They're going to be switching in the sort of the kilohertz range, 1 to 5 or so kilohertz. The radio frequency pulses are going to be sort of in the neighborhood of 64 megahertz and sort of kilowatts energy strength. And when I first heard of this technology in 1983 when I was finishing my master's degree, my first thought was, as an electrical engineer, is I can understand the instrumentation. I know how to build essentially coils and amplifiers that will meet every one of the requirements I have there. Okay? So I wasn't afraid of the instrumentation, but what I recognized was I didn't know the physics, but I was brave enough to say I can learn that. So if we talk about this 1.5 Tesla field, as I said, it's basically a 30,000 times the strength of the main magnetic field. In terms of some of its electrical characteristics, it's basically a solenoidal design, and the number of, or amount of henries, if you will, of measures of inductance of this particular device, it's somewhere in the neighborhood of 0.5 to 1 Henry. That's a big inductor, okay? A big freaking inductor, okay? Now, in order to get enough current flowing through that, I need something in the neighborhood of 400 amps or so and about 6 miles of wire, okay? So 6 miles of wire, if it wasn't cooled down to superconducting temperatures, you might worry about how much power dissipation or heat energy might be dissipated in this long length of wire carrying 400 amps. By using superconducting wire, there's no dissipation of energy, and therefore, once we get that 400 amps of current flowing in it, we can essentially unplug it from the wall, and it will stay there persistent as an electromagnet for years and years and years, as long as I keep the liquid helium imposed in it. Now, the other thing I have to recognize is to make this magnet, not only do I need something in a neighborhood of 6 miles of wire and some power supply that's going to give me 400 amps of current or so, I also have to remember that force is I cross B, okay? So I have current running through each of these different loops of the magnet. I'm just going to approximate a solenoid in this particular case. So I have lots of current through it. As soon as I put current through those loops, I'm going to create a magnetic field, and the force that's generated from that field is equal to I cross B. So the forces generated within an electromagnet that I use for MRI is in the order of hundreds of thousands of hundreds of kilonewtons of force inside of the magnet. So not only do I need to have these loops of wire made in such a way that I can manufacture it and make the solenoidal magnet that's going to create the field, but that design also has to be able to withstand the forces that are going to be created internally and hold the liquid nitrogen and the liquid helium I have to keep the wire cool. So this is a really cool design challenge for anyone who's interested in that kind of stuff, because you're essentially dealing with low frequency kind of devices, but also extremely high fields. Now let's talk about where the signal comes from. We all know that water has 2 protons in it, 2 hydrogens, 1 oxygen. And let's look at some of the sort of characteristics of that hydrogen atom, if you will. Clearly at the center we know that there's going to be a proton, H1. We have electrons going around the outside of that particular thing. And if I look at some of the properties of the protons, I have mass, I have charge, and I have one quantum property that I want to share with you, and that is spin, angular momentum. Okay? So I think everyone's always comfortable with the fact that protons have charge, and I think everyone's pretty happy with the fact that they have mass. Not everyone is really comfortable with the fact that they have angular momentum. Okay? But it's these 3 properties that come together that give rise to the magnetic properties that my proton needs to have in order for me to do NMR. So that mass and that charge, or that mass and that spin, what are those 2 things going to create for me? What if I had a loop of wire, for example, with current running in it? What would that produce? The dipole, right? A little magnetic moment, okay? So the same thing is going to happen with our proton. The fact that I have charge and I have spin is going to create that little proton having a magnetic moment associated with it, okay? So if I put that little magnetic moment inside of a magnetic field, what would you expect it to do? It's going to line up. You'd expect it to, at least, and that's actually what's going to happen. So we can basically create the relationship that the magnetic moment that we're interested in is related to a gyromagnetic ratio and the angular momentum that this thing has because it's spinning. There's just simply some relationships there. So it's the magnetic dipoles of proton in hydrogen nuclei of water molecules that we're going to use almost exclusively 99% of the time, 99.9% of the time when we talk about MRI. Now there's other nuclei that have magnetic moments that we could be interested in. Carbon-13, phosphorus-31, O17, sodium-23, etc. Okay? But why are we going to pick water? Why are we going to pick protons? So now you guys can be biomedical engineers for a second. Okay? Why would I pick water? Why would I pick protons? Oh, come on.
You have a
A lot of them. 80% of my body is water. Every water molecule has 2 protons. There's more protons in me than anything else. So if I'm going to attack anything with NMR, I'm going to go after water first. I'm going to go after protons first. So right now, why is it that you don't have any little magnetic moment associated with you? You're in a magnetic field, 0.5 Gauss. You all have tons of protons in you. Why is it that you don't have a little magnetic moment? Why is it that if I had a compass here, everything wouldn't be pointing towards you guys? It's too weak. And the reason it's too weak is if I look at how much magnetic moment that little proton has, it's incredibly small. And if I look at its ability to line up with respect to the Earth's magnetic field, that alignment is in competition with the thermal energy of the body. There's enough thermal energy of our body shaking up those protons that as much as they would like to align, the thermal energy of the body is simply knocking them around and they can't individually. But if I look at it sort of in the situation where I jump inside the magnet, let's say I took Dr. Leparo and I took him over to radiology and I threw him inside a main magnetic field of a 1.5T scanner, how many of his protons are going to line up then? We have a completely different competition now, right? My main magnetic field is 30,000 times stronger. The competition that used to exist between the thermal environment of the body and the magnetic interaction between the proton's magnetic moment and the field, how many of them are going to line up? Almost none of them, okay? It's essentially the ratio, if I look at this, is approximately 7 per million per Tesla is the net alignment. It's an incredibly small number of my protons are going to be able to line up with respect to the main magnetic field. And you may say, like, well, those are pretty crappy odds, Jeff. You know, how is it that we're possibly doing NMR imaging? And the reason we can do it is because there's so many protons in our body. The fraction's small, but the number is high, and the number is sufficiently high that I can get a signal. And we're going to talk about what that signal is in a second. So what would be the two things I could do to Dr. Leparo to make it so that I could get more spins to align inside of him?
First thing you got to do is get me there.
Yeah, okay. So the three things. First is get him there. What are the two other things I could do?
Cool him down.
I could cool him down, make that thermal energy not quite so strong. And if I cooled him down to absolute zero, I would get all of his protons to line up independent of whatever field I put him in. Now, I wouldn't get many referrals from a radiology perspective because obviously he's not going to come back again. But this is one of the things I can do is I can make my sample colder, or I can do what? Make my field stronger, okay? And this is one of the things that's pushed the development of MRI over the years. When I first got in the field in the 1980s, common magnetic field strength was 0.15 Tesla. 1.5 Tesla, 10 times higher, is very common today. 3 Tesla is probably what's being sold more than anything else. And there are probably on the neighborhood of 50 7T magnets out there in the US, or in the world. So going to higher fields gives rise to more and more of these protons aligning. So let's look at what happens not just with the magnetic moment, because all we've talked about there is the fact that we have, you know, this little bar magnet associated with our proton. We also have to consider the fact that these protons have spin, okay? They have angular momentum. And if I think about what sort of the equations of motion are of this proton's magnetic moment in a magnetic field, keeping in mind that this magnetic moment is spinning, it's going to be very similar to the equations of motion of a top in a magnetic field or in a gravitational field. So imagine I had a top and I got my top spinning, and if I lined that top up with the gravitational field, it would just sit there like this. But if I tipped that top a little bit from the gravitational field, it would precess. It would simply wobble about the gravitational field. And because the equations of motion of my proton are so similar, that's exactly what my magnetic moment of my proton is going to do about the main magnetic field as well. It's going to precess about the field. So that's individually. Now I also said that there's millions of them, and on average the one component they're all going to have in common is a component pointed along the main magnetic field. Okay? So here's, if I were to sort of describe it, this is the motion of my magnetic moment about the main magnetic field. Clearly they're not drawn to scale because this is on the order of femtotesla, and this is on the order of Tesla or so. Incredibly small magnetic moment, but it precesses about the field. Now I have zillions of these things, and the one component they're all going to have in common is something in the z direction along the main magnetic field. So this creates a little bit of a challenge for me, in that while I have this magnetization that will precess about any field that it sees, the challenge is it's a needle in a haystack problem. When I look at the aggregate of all the protons for Dr. Leparo, that net aggregate, that bulk magnetization, is going to be pointed along the same direction as the main magnetic field. The total amount of magnetization is very small. It's pointed along something that's really big, and therefore, in its original orientation, I'm not going to be able to detect it. Somehow I needed to get it to change its orientation. Now the key here is that these things are wobbling, they're precessing, and they're precessing at a characteristic frequency given by omega equals gamma b, where omega is the resonant frequency. You may have asked yourself, what's this MRI stand for? I already talked about magnetic. We're now going to talk about resonance, and in a little bit we're going to talk about imaging, okay? So the resonance thing is sort of what's the frequency that these things are precessing at. So if this is my magnetization, the white thing, along the direction of the main magnetic field where it starts out originally, if I can create a yellow field that's rotating at the same frequency that the spins are processing, my magnetization will tip over, okay? Because my spins, my protons, are going to precess about any field they see. They're aligned like this. They're happy precessing about the field. If I add an additional field, they will begin to precess about it and tip over, okay? I can then shut that field off because I've caused those spins to change their orientation. So watch this again. So the question you should be asking yourself as electrical engineers is, how do I create that oscillating magnetic field? Because from your perspective, it's oscillating at 64 million times a second. You're electrical engineers, I'm sure you could do it, because we've done it 20 years ago, okay? I can also describe this precession in what I call a rotating reference frame. That is a reference frame that's unique to me, okay? So from your perspective, you see the precession or the oscillation of this field. From my perspective, that's rotating with the magnetization, it looks like a constant, and all I have to describe is the tipping. So almost everything we do in MRI is what we call in the rotating reference frame, from the perspective of the protons. We only need to describe the tipping. It's a lot more complicated looking in your perspective, the laboratory reference frame, than it is in mine, in this rotating reference frame. So the question is how do we create that rotating magnetic field? Well, at 1.5 Tesla, the resonant frequency is 64 megahertz. And so somehow I must be able to turn it on and off. That is, create the start of the tipping and stop it when it's tipped far enough. And if I look at sort of what I'm going to need for that, I'm going to need a loop of wire in order to drive current in and create a magnetic field. And if I look at sort of some back of the envelope calculations, the strength of that field is going to be in the neighborhood of about 1 microtesla. Really small. But things are processing fast enough that my spins are going to trip really quickly. I need an amplifier to create the oscillating current that's going to get driven into that coil of wire. I need a mixer in order to give that RF pulse some shape, maybe a sync shape or something like that. And you might be able to be sort of thinking, gosh, you know, I'm going to need 5 kilowatts RF amplifier. I need a mixer to give me some amplitude modulation. I'm going to be at 64 megahertz. That sounds an awful lot like an AM radio station. And in fact, every MR system out there has a little AM radio station operating at 64 megahertz or 126 megahertz or whatever, inside of it to simply broadcast that RF energy into the patient, cause the protons to tip over, and a few microseconds later, we're going to actually detect that. Now, we know that this is sort of the equilibrium orientation of our protons. As soon as we tip them over, we've destroyed that equilibrium, and that signal, that magnetization is going to go away. Its equilibrium is back like this, and so it has to return at some point, and it may also decay in this detection plane as well. And so if I look top down on what happens to my magnetization after I've tipped it over, it will decay in time, and it will regrow along this orientation. And it's these two parameters, T1 and T2, that I'm going to capitalize on later in order to get contrast. We're not going to talk about that today, but these are the two fundamental parameters in MR we use to get contrast. So generating a signal is all well and good, but that's not imaging, right? So I said I have Dr. Leparo, I put him inside the magnet, I send out a pulse of RF energy, all the magnetization from his body tips over, I induce a voltage in a coil. That's not imaging. I need to figure out where that signal comes from, or alternatively, selectively excite one location over all others. The one thing we know is that the spins are only going to get tipped over if they're on resonance. If the frequency of the RF pulse is exactly the same as the frequency at which they're processing about the field. So imagine that I vary the strength of the field from the head to the foot. Somehow I turn on a gradient that makes the magnetic field strength at my head stronger than at my feet. That means the resonant frequency of the water at my head is at a higher frequency than at my feet. I have a one-to-one mapping between frequency and position now, right? I have a linear variation in the field. That means I have a linear variation in the frequency that the spins are processing. And therefore I can apply an RF pulse at a specific location to determine which spins get tipped over. This is starting to sound like imaging, because I've been able to excite or selectively determine where my signal is coming from on one axis of the body. So that's the process of slice selection we're going to use. But to do that, I need to create a gradient, okay? A linear variation in the magnetic field. This is simply a representation saying that the strength of that frequency is proportional to the main magnetic field, how much variation there is linearly, and where I am along that gradient. Now let's look at what happens to 3 different positions that are within that selected slice now, and I turn on a gradient left to right, for example. Okay? So I have 3 different positions, black, red, and blue. I tip them over. Each of the different positions are at a different frequency, right? And therefore, they're going to induce a different frequency in my receiver coil following the RF pulse. Just like I had a one-to-one mapping in order to do my slice selection, I'm going to have a one-to-one mapping to create a difference left to right. All of these 3 signals get induced in my coil at the same time. My coil is essentially a big integrator. So if you were given the task of finding out which frequencies were present in this signal, what would you do? It's a time domain signal. Right there. Okay, do a Fourier transform. Sample the signal, do a Fourier transform. Fourier transform will extract for me which frequencies are present, which essentially is saying in which positions do I have signal, because I have one-to-one mapping between frequency and position. And so I'm getting really close to imaging now in 2 dimensions. 1 to give me a slice, 2 to give me left-right. And in fact, that's what we do. We do a Fourier transform on my induced voltage in order to create some information about the spatial position of my signal. So let's look at these magnetic field gradients for just a second. So initially, the coil operation in terms of my detector is going to go from hundreds of volts, as I said before, into nanovolts in the order of microseconds. The proportion or the strength of my, this actually shouldn't be magnetic field gradients, this should be the actual coil used to detect the signal. Okay, so I apologize. So I know that the frequency of my spins, the frequency of my magnetization is going to be dependent on where they are, where the spins are located. I know that when I transmit my RF pulse, it's going to be hundreds of volts, but the detected voltage is going to be nanovolts. My amplitude is going to be in the proportion to how much magnetization I have. But I think all of you would agree that sort of trying to do A to D conversion on a nanovolt signal is going to be difficult, if not impossible. So what do you need to do? Got to come up with some amplifiers to get that signal up into the 5 to -5 or 10 to -10 volt range. And those amplifiers better be very low noise, because I've only got an SNR of sort of 10 to 100 or so to begin with in my signal. And so the types of technologies I need are gain stages. They're ultimately going to, when I cascade them together, going to give me hundreds of dB. I'm going to need some type of demodulator to take my 64 megahertz signal down to some frequency range that I can easily detect with an A to D converter, maybe 30 megahertz or so, and then sample at twice the Nyquist rate. I'm going to need other types of technologies as well to couple that signal from my patient and my coil all the way back into these demodulators and receivers. Now, if I figure all this stuff out and propagate a bunch of stuff together, the form of the equation in relationship to these gradient waveforms that I apply can be expressed something like this, where this thing represents Dr. Leparo. This represents how I turn on and off my gradient waveforms. This represents spatial position. And this basically is the integration that the coil does. That is dx dy and this double integral here. So I have the signal from Dr. Leparo and the influence of these gradients. Now if I look through this and sort of start lumping some parameters together, what I can show is my signal is essentially the Fourier transform of the object. So I've been doing this for like 20 some years now, and this is still freaking amazing to me, that the signal that I detect is the spatial Fourier transform of Ken. Okay? I have to sample my signal. I have data that I'm collecting in the Fourier domain. How would you reconstruct an image that's the Fourier transform of the object? The signal I have is a Fourier transform. I don't have the object yet. I want to get an image of Dr. Leparo. How would I do it? I'm going to do a Fourier transform, right? That's how we do reconstruction in MR. We do a two-dimensional Fourier transform on the signal we detect. It's amazing, but it works. It's still... So here's essentially what this equation says. We have the object, we're multiplying by a sine wave. In one case, a sine wave going left to right. In the other case, a sine wave up and down. And we're collecting this in a two-dimensional Fourier space representing how many cycles per centimeter left to right or how many cycles per centimeter up and down we're collecting at any given time. These are simply the wave functions that we have in MR. So the way we're going to reconstruct it, as you guys already predicted, is by doing the inverse Fourier transform. And so this is an incredibly cool MR or signal processing problem that any of you who are electrical engineers should be really interested in. And that is, how do I play out my gradient waveform, okay, in order for me to sample K-space, this Fourier transform space? Because after all, you know that I could sample it in sort of a uniform grid, and I could easily do a discrete two-dimensional Fourier transform on that grid. But that may be the least efficient way for me to cover that space. There may be other paths, other ways to walk through that space that are more efficient, that require me to use a different type of reconstruction than a simple two-dimensional Fourier transform, and we're going to talk about that here in just a second. So think one-dimensionally, and think of a spectrum, okay? We have minus Fs over 2 to plus Fs over 2. What's right at the center? DC, right? And so how much variation, how much information do I have about the variability of a signal do I have at DC? None, right? That's just the average level, okay? So by analogy, okay, when I talk about this Fourier transform space, because this is telling me how I'm collecting my signal, okay, I collect my signal in the Fourier transform space. This is the center of K-space. It's sort of the center of the spectrum. It tells me what's the average value in my image of Dr. Leparo, okay? And so I've taken this one point, actually it's a couple points, and I've reconstructed it. And I think you'd all say, you know, there's not much detail there, but I sort of give some information about the average value in that image, okay? But let's look at what happens as I sample more of K-space. Okay, so what happens right away? You can now start to see some contrast between different locations, right? So the center of K-space is where I have contrast information. What am I going to have if I go higher, further out, higher frequency stuff? What information am I going to get? Edges. Who said edges? Excellent. Okay? Edges. Edges or resolution. So let's go further out in K-space. You can see as I go out, now you can start to see the edges between the different tissue parts as well. So my center of K-space is where I have contrast. My edges of K-space is where I have resolution. So if I look at an MR pulse sequence, what I essentially have is something that's going to allow me to do slice selection and figure out which location I'm going to image. But then I'm simply going to play out some gradient waveforms in other directions, left to right, front to back, for example, that allow me to simply define what row of K-space I'm acquiring, and then as I'm sampling my signal, move left to right across K-space. And then a few milliseconds later, I'm going to move down to the next row of K-space, acquire that, the next one, the next one, the next one, until I fill up my data. Ah, shoot. Okay, so let me go back. Okay, so that's what K-space looks like. This is what MR data looks like before I do the reconstruction. Two-dimensional Fourier transform of this is the image of Dr. Leparo that we're all looking for. And here's what the gradient waveforms do. They simply play out. They define a different line for me. As I'm moving across a given line, I'm sampling my signal. That's moving me left to right. And I'm simply reconstructing my image at every step of the way. So let's do this again. At the edges of K-space, or at the limits of K-space, all I get is edges. When I get to the center, I'll get contrast. And then as I go further out, I'll get the rest of my contrast. So the center of K-space, contrast, edges. So let's talk about the gradients for a second again. These things are millitesla in field strength. Now remember, my RF pulses were microtesla. My main magnet was Tesla. My gradient coils are sort of in the neighborhood of millitesla field strength, actually millitesla per meter. They're going to be oscillating in sort of the kilohertz frequency range. I'm going to have 3 of them in each MR system, one for Z, one for X, one for Y. That's what allows me to do my imaging. My winding pattern, that is how I actually create the coils that are going to create these magnetic fields, are based on a target field approach that allows me to also incorporate active shielding. That is, creating no spurious magnetic fields outside of the coils themselves on the conducting surface of the magnet. I'm going to minimize my amount of eddy currents. So if I think about my imaging time in MRI, basically it's typically long, and we can only do essentially one of these lines at a given time. And as we saw before, my signal decays away and there's a bunch of nuisance factors that really sort of challenge me in terms of how I'm going to do my acquisition. So I have to repeat this acquisition over and over again. It takes time for my signal to recovery. And since we can only get one projection per repetition time, we basically get a one-dimensional representation of the object, let's say along the x direction. And so if we need to do this multiple times, my scan time is simply equal to the amount of resolution I need times the amount of time I need to perform each acquisition. So this particular image is 128 by 128 pixels. If the lights were down a little bit, you'd see it's a heart. If the repetition time between each acquisition was 10 milliseconds or so, my total acquisition time for this image of the heart would be 1.3 seconds or so. And this is too slow to acquire the data for a beating heart. The image would essentially be blurred. Okay? So our challenge then is to speed up the image acquisition time. Well, one way would simply to go to lower resolution, yet use the same repetition time. In this particular case, I've used, or Mark, my colleague, has done this for me, used essentially half the resolution, and you can see that my image is quite a bit blurrier than it was before, but my acquisition time is only 640 milliseconds now, getting closer to what I might need, but the spatial resolution has really been compromised. So I've lost resolution that would otherwise be useful. Another way I could do this is to actually use the technology I have available to me to reduce the repetition time, play out those gradients much, much stronger and over shorter periods of time. And if I did that, I might be able to reduce my acquisition time by, let's say, an order of 4 or so. That would get me down to an acquisition time of 320 milliseconds or so. This is almost fast enough to image a beating heart. But what limits our ability to reduce the repetition time? As I said before, we have to turn on and off these gradients. And most of the time when we turn them on up to some value, turn them off, relatively slow process. If I want to speed it up, for example, you can see how I can reduce the total time by a factor of 2, but I have to keep the area the same. And that's one of the key things in MR. For me to get the same resolution, it's a question of the gradient area. If I can do it faster, that's fine, but I need to keep the gradient area the same. And the implication here then is, if you look at sort of what we've been able to do over the last 20 years or so, 10 millitesla per meter was about what we had when I started in the field years ago. It would take a millisecond to rise up to that limit, and I could turn them on and off at about 1 kilohertz switching rate. The highest gradient strengths ever used were developed in 1998. This was in Mark's lab. 50 millitesla per meter, actually quite a bit higher, about 25% higher than we even use available today. They could turn on incredibly fast in 60 microseconds switching time, and they could oscillate at 10 kilohertz or so. Incredibly strong fields switching incredibly fast. Sounds pretty cool, okay? But why haven't we gone further than that? So let's look at the implications of going to twice as high in terms of our gradient strength and 4 times faster in terms of our gradient rise time. That is, reducing everything by a factor of 2. Reducing those slew rates by a factor of 2, but we still have to go twice as fast. So pretty quickly we reach the limits of what we can build and what stimulation the human can tolerate. So our rise time, I mean, after all, these are just coils. Our rise time from our amplifiers is proportional to voltage, L di dt. The strength that I can achieve is proportional to the current that my amplifier can provide. And therefore, if I look at sort of for an R-fold level of acceleration, I need R squared times higher voltage and R times higher current. And therefore, my power to go faster by a factor of an R actually goes up by R to the 3rd power. So there's some practical implications of this. If I look at the gradient systems I already have available today in my MR systems, the amplifiers are already available to provide 2,000 volts and 500 amps. That's about 1 megawatt per axis. okay? Now these are audio amplifiers, okay? So this is like Rolling Stone kind of audio amplifiers at 1 megawatt of sound, okay? And we have 3 of those per MR system. So we have 3 megawatts per MR system. If I want to go twice as fast, okay, that means I need to have 8 times higher power per axis, or 24 megawatts of power per MR system. If I want to go 4 times faster, I need 192 megawatts. And we quickly go from the setting where I can provide it in a modern MR system today about 1 megawatts per axis to needing something like a nuclear power plant or so per MR system, which is simply infeasible. And finally, we sort of get to sort of the physiologic limits, and that is the switching magnetic fields induce electric currents in the patients. You know, as these electric fields are turning on and off, our body is conductive, and therefore we're creating currents inside the body that cause our physiologic systems in the body to sense it. And so the state of the art that we have already available today is right at the limits of what a patient can feel, and going higher than that would go higher than what we could essentially tolerate in patients. So we need something different. And that's where the technology that Mark created called parallel imaging comes into play. Now previously, essentially all scanners used volume coils. That is, RF coils that were made to cover a volume, a head, a body, or something like that, for example, and to cover that region in a homogeneous manner. Now one of the things we can look at is the received noise, that is the induced noise in the coil from the patient, from the subject, is basically dependent on the size of that coil. If I can make my coil smaller, I'm going to have less noise. So big coils give lower SNR, smaller coils give higher SNR. So if I could, I would like to move away from this paradigm of sticking a head inside of a single coil and maybe using an array of them. So what we're going to do is look at how we might be able to combine many small coils together where each of them has been designed to have some local optimum SNR. Now clearly this is going to have implications in my system design. I used to simply need one plug in the coil, put the person's head in it, and get that signal induced, transmit that signal or hook that system up to the system, transmit into the patient, listen to the signal back, demodulate that signal and reconstruct it. If I'm going to have multiple coils now, I need to have multiple receiver channels as well. And each of these coils may interact with each other simply because of mutual inductive coupling. And so there's a bunch of electrical engineering challenges I might have to encounter. But the idea here is if I can use equally, or basically an array of coils that all have some local optimum SNR, I can get some optimal SNR of the whole object, even though my system may be somewhat more complicated. And here you can see an example where you have an array of coils that are around the head and an array of coils aligned along the spine. So if I look at sort of modern MR imaging coils today, this is from a company here in Cleveland called QED. From the outside, it looks relatively simple. It looks like I said before, a device that you're going to plug into my system, and I'm going to transmit and maybe receive, and there's a simple couple different connectors associated to it. But if I look inside, there's actually a huge amount of technology. Inside are approximately 5,000 parts, each of them with 10 ppm tolerances. In this particular case, we have arrays that may range between 16 to 32 channels, each of them requiring low noise, low impedance preamplifiers, balins, geometric decoupling, etc. This is a field ripe for electrical engineers. Now, if I go to the research setting where I don't go to the 16 to 32 channels, I may go up to as high as 100 different coils in that particular array. And you can see my challenge is to take those nanovolt type signals that are induced in each of the different receiver channels, get that out to the system in some type of system that has reduced interaction between the coils as well as maintains the tolerance. But here's why we do it. If we look at the sort of the type of image quality we would get from a body coil, it's something like that, and the array coil gives us something like this. Now the challenge is we need to expand the system and have multiple arrays, but the neat thing is each coil array or each element of the coil essentially carries some type of spatial information with it. That is, this coil over here has some information associated with detecting this part of the object. This coil over here carries some information because it doesn't have sensitivity everywhere but locally. Now I know I'm running out of time, but the basic challenge we have then is to see if we can come up with some type of imaging technology in which a volume coil sees in the case where a volume coil sees the entire object, When we do our acquisition, we encode the whole object in our acquisition time as we saw before. But if I could make receiver coils that only see a limited area, I might be able to reduce my acquisition time. In this particular case, for example, imagine a receiver coil that only sees the top half of the head. A second coil may see only the bottom half. And therefore, in half the acquisition time using an array of 2, each of them receiving independent regions, I can put them together in half the imaging time to create an image. Now, the basic idea here is the fact that there is some special mathematics that relate to these particular devices and allow us to put these coils together. Because after all, it would be impossible to make 2 individual coils that each see distinct non-overlapping regions. Once we have some level of interaction, we need to somehow account for the mutual interaction between them. Now, I'm going to sort of blast through this, but the neat thing is those coils essentially give us or create a convolution in K-space. That is a smearing of information from one location to the next. Okay? So our challenge then is how to extract from that information then what that coil information is. So in this particular case, the convolution moves information all around K-space, whether I have data in those lines or not. So in this particular case, for example, maybe I didn't collect this line or this one or this one. There was still a blurring associated with that coil from this location to this one and vice versa. But I can also add multiple coils, or the fact that there are multiple coils there, for example, for me, and therefore fit a relationship across the different data that I see. In this particular case, what I'm going to do is collect some data that allows me where I don't skip a given line. I then fit the data to a given relationship, which allows me then to fill in the gaps of the data that I didn't collect. And I can do that across all the different coils. So in this particular case, I'm using the relationship that exists between coils and the convolution from them to allow me to reduce the amount of data I collect. And therefore, I can accelerate the scan time in ways that I couldn't do with gradient waveforms alone. So in this particular case now, we can do real-time imaging, 1.5 Tesla, using 32 different receiver coils around the torso, around the heart, with 4-fold acceleration compared to conventional imaging. This is what would have previously required me to have a separate nuclear power plant just to provide the system. We can do it now with low frequency, low amplitude electronics associated with the receiver arrays. Now, I don't have time to talk about the big signal processing opportunity, but basically that is, instead of going through a rectilinear type scan that we saw previously, to use other trajectories. Maybe a radial acquisition like Dr. Lauterbur did in 1972. And you can see in this particular example where I'm using a radial scan and I'm covering my K-space in a radial type acquisition, that my resolution and SNR relationship is different than what I had previously when I did a rectilinear scan. So I'm going to show this one again, because essentially what you'll see is I get resolution and contrast right away because my data is always hitting the center of K-space a little bit in this type of radial acquisition. Now there's other radial patterns I could use too, ones that are a little bit more interleaved, for example. And you can see in that particular case, I get my SNR and resolution almost immediately. Completely different way of covering K-space, however. And so to do that then, obviously my data does not fall on an equally distant rectilinear grid. I can't use a Fourier transform, but I have to do something, or I may need to do something like convolution gridding to take that data from its existing locations in K-space to distribute them onto basically a K-space grid that is rectilinearly sampled. And then do the reconstruction. So all of this stuff allows me to sort of have scan plane flexibility, high SNR, and those kind of things that I would like to have in the imaging modality. So I can get all kinds of different contrast. I can do things with my computer science colleagues, like do MR angiographic images without injecting dyes, for example. All of this with the MR technology that's available today. So in summary, I think there's lots of research opportunities, both in the graduate program and also career opportunities for electrical engineers and computer science majors in MR, whether it be magnet design, whether it be the RF transmit or receive coil arrays. All of these require unique contributions and interactions between people like yourself, people like me in radiology and biomedical engineering, and our physician colleagues as well. There's numerous opportunities in terms of signal processing as well, we're talking about microvolts and nanovolts and 64 megahertz signals in these difficult case-based relationships. But the neat thing is, it's all essentially things that we've learned about previously in terms of our Fourier transform experiences. So anyhow, that's sort of a little introduction to some of the opportunities you guys have in terms of EECS and MR imaging. There's other opportunities in other fields like PET as well, but since Mark and I do MR, I thought I'd try and focus on that today. Thanks a lot. So I know I ran a little late. Any questions? Sure.
This was excellent in terms of the issues in signal processing, but you didn't really touch computer science. What type of problems do you foresee in computer science?
I mean, for us, the big challenge, I mean, there's a couple big challenges. One is just reconstruction time. You know, it's, you know, we have benefited from the increased performance of computers over the decades, but how much data in a 32-channel array do we collect in? Yeah. So we can image much, much faster than we can reconstruct data. You know, because we have to then take that across all those arrays. You know, if we do a non-rectilinear acquisition, we need to do the parallel imaging to, you know, separate, to create the data we didn't acquire, reconstruct it, and that kind of stuff. So.
And it is done in spatial temporal space, right?
Yeah.
Or time and spatial.
I can add that right now I'm over here because my computer back on my desk, which is an 8-node, 3 gigahertz machine, is processing a data set that it took 500 milliseconds to acquire, and it will take 2.5 hours to process the image.
So if you can improve on that time of reconstruction, that would be a accomplishment.
So Mark had a student for a while who, from this department, who was looking at graphic processing units, so graphics cards to do the reconstruction, because it's just arrays of numbers, for example. You know, so that's an example, for example, where computer science folks have made dramatic contributions to what we do. Even this kind of stuff I was showing here, for example, with the MR angiographic images, for example, and maximum intensity projections. Where is that? Was it before that? Is another example where, for example, we can set it up to have, you know, so the acquisition looks like this, and the areas in which there's blood flow are brighter than normal tissue. What we then need is algorithms that go through that data set to sort of project it onto, from a given orientation, for example. So we can, you know, we're good at acquiring the data and reconstructing the images in some case, but then there's all kinds of applications like this. The diffusion, the other application that we showed earlier, which was these sort of tractography maps, is another example where, gosh, why can't I find it? You know, again, where the technical challenges are really phenomenal to be able to process this huge amounts of data. To do this type of acquisition, we have to do an acquisition that's encoded for sensitivity to motion in this direction, then this direction, then this one, then this one, and then the eigenvalues, and, you know, we sort of use that to sort of create these maps.
Let me just add too that this is a place where computer science can actually impact healthcare worldwide. The method that's going on in my computer right now would potentially change somebody's life, but that 500 millisecond image is actually a series that I took over a minute, and so it takes me a couple of weeks to get the full data set. The patient could be dead by then. So here's a case where we're really limited by the computation. If you fix the computation, you impact healthcare. This is pretty rare.
Yeah. There's other applications too, like Mark, in the one example that we had here, where we had, for example, an acquisition that showed that beating heart. That's done in real time. So that's a patient that we don't have to hook up ECG leads to the patient, for example. The patient doesn't have to hold their breath. You know, people who are sick can't hold their breath at all. You know, you get a patient over there that has congestive heart failure, you know, oxygen saturation of 70–80% in their blood, they can't hold their breath. And so normally, a normal cardiac MR scan, you couldn't even do it. Now with this technology, you don't have to hook them up to an ECG. They don't have to hold their breath. You just image as fast as you can and get the data. The reconstruction can be longer in that application. The real-time part isn't as important because we have the data. You know, but again, there are going to be a number of applications where computer science has tremendous implications in what we can do in healthcare. Thanks a lot. Really appreciate it. Thanks for the chance.